On to heterogeneous catalysts. Now we're still talking about transition metals as catalysts and their variable oxidation states that allow them to do that. But what's the difference between a heterogeneous catalyst and what we talked about in the previous tutorial, which was a homogeneous catalyst? As you've probably guessed, a heterogeneous catalyst exists in a different phase. That means, solid, liquid, or gas to the reactants of the reaction we're trying to catalyze. Now, most of the time, this is usually an example, let's say using a solid transition metal in either an aqueous or a gaseous reaction. And we've seen a couple of examples of this already at GCSE, would you believe? And we're going to use those two examples to help us explain what's going on in terms of these heterogeneous catalysts. First example here is iron, solid iron in the Haber process or Haber process, whichever you prefer. Now, we're all familiar with the Haber process. N2 gas plus 3H2 gas in a dynamic equilibrium with 2 ammonia, 2NH3 gas. So it's a completely gaseous system, this, but the solid iron is put in there into the reaction chamber because it facilitates the reaction. It catalyzes the reaction. It lowers the activation energy for the reaction between nitrogen and hydrogen to produce the NH3. Now, the ins and outs of this, we do not need to know, but things to point out here. They tend to use powdered iron, maximizing the surface area for the efficiency of that catalyst. Okay, so while you've got, you wouldn't just put like just a lump of iron in there. You grind it up, they coat it on a large surface area material just to increase the efficiency. Like I said, we don't need to know the ins and outs of this. Just know that it's a solid example, if you excuse the pun. Second example is V2O5, okay, vanadium 5 oxide in the contact process. Now, if you remember, the contact process is where we actually make sulfuric acid, a really important process. Now, just one part of that process involves the reaction between sulfur dioxide, 2SO2, and oxygen. So 2SO2 plus oxygen, gaseous system again, dynamic equilibrium again, producing 2 sulfur trioxide gas. So it's a gaseous system, but again, we've got a solid catalyst, V2O5 sat in there, acting as a catalyst, okay, lowering the activation energy and increasing the rate of reaction. Now this, I think we do need to know this. I think we should learn how vanadium 5 oxide acts as a catalyst in this reaction because it does come up quite a lot in the exams. So the first reaction that I wrote here, that's the overall reaction between sulfur dioxide and oxygen to make sulfur trioxide, and I've just stuck the V2O5 on the top there. But the catalyzed reaction is a 2-step process, and we can show how the V2O5 actually acts as a catalyst here. So the first part of the reaction is the sulfur dioxide reacting with V2O5 to give SO3 and V2O4. So you can see here how the V2O5, which I've done in red to show you that it's regenerated later, actually changes oxidation state. The oxidation state of the vanadium in V2O5 is +5. The oxidation state of the vanadium in V2O4 is +4. So the vanadium's been reduced here, again, as a transition metal, using its ability to exist in different stable oxidation states. So that's the first step. Second step here is where we have 2 V2O4, okay, so that we've made during that first reaction, reacting directly with oxygen to regenerate that V2O5. So we end up with 2 V2O5 there, okay? So you can see how that vanadium 5 oxide is used. Its oxidation state changes from +5 to +4, but then when it reacts with the other reactant, V2O4 plus O2, it actually gets changed back to +5. So this is a really good example, again, like in the homogeneous catalyst tutorial, of how the variable oxidation state of a transition metal allows it to act as a catalyst, as an intermediary in a reaction. And of course, for both of these examples here, they show that the activation energy is lowered when a catalyst is used. This is the path of least resistance. This happens anyway. But if we can use vanadium 5 oxide, it lowers the activation energy in a similar way to the previous tutorial and essentially ends up with a greater rate of reaction. So this is a really important example. Now, one thing we do need to talk about here with a heterogeneous catalyst is how efficiency can change. Now, a catalyst doesn't get chemically changed during the reaction. We can see that with the regeneration of our V2O5 here. But the thing is, they don't last forever. We need to talk about efficiency, the efficiency of these solid catalysts in these heterogeneous systems. So we've got a solid catalyst in these two examples in a gaseous system. So how do we improve efficiency? Well, as I mentioned previously, increasing the surface area. So using ground up iron or using ground up V2O5 actually increases the surface area, and therefore it's more efficient. It allows a greater surface area for the reactants to bind to and undergo the reaction that they need to. Another way that industry can achieve this is by taking that solid catalyst and spreading it over what's known as a support medium. And that is literally something that can support that powdered catalyst. It's an inert framework. So if you build like a honeycomb framework and then you can like powder spray it with, let's say, iron or vanadium oxide, just covering the surface, that's going to really increase the efficiency of your catalyst as the gases pass through that honeycomb framework. So in other words, they can use less catalyst over a large area. It's all about saving money, okay? How can we make this iron or vanadium oxide, spread over a large surface area without losing loads of it? Well, that's one way of doing it. So creating this inert framework or support medium and like I said, powder coating it with your catalyst, maximum efficiency, minimum cost. One last thing to mention here in terms of efficiency is that efficiency decreases over time due to something called poisoning. Now, this occurs as impurities. So you're always going to get other things maybe present in the reaction chamber. As hard as you try, you're always going to get other things in there. So this occurs as impurities stick to the surface of your catalyst that you've spread, nice and thinly over this support medium. And what that does, or what they do, is block the interaction between the catalyst and reactants. So this term poisoning is a really important term. So over time, let's say the iron catalyst in the Haber process, you're going to get some impurities stick to it. Okay, maybe small particles of carbon or something like that. Anything that can get in there and stick to that support network and block that catalyst from working. So they do decrease in efficiency over time. Of course, every effort's made to ensure that the only thing in there is your reactants. But you know what? It happens. So efficiency decreases over time due to poisoning, and it's impurities blocking the catalyst from reacting with your reactants. Okay, so heterogeneous catalysts, different phase. Two major examples. One, I would kind of remember these, okay, because if you're ever asked to give an example of how a heterogeneous catalyst work and how transition metals use their variable oxidation states in order to catalyze a reaction, this is the one you need to go for. But then they may ask you questions about the efficiency of catalysis as well, and these are the headlines that you need to remember. Make sure you subscribe to our channel so you can keep up to date with all our new content. If you like this, you'll love our free trial. Click the link and check it out. You've now got two choices. You can wait and see what YouTube randomly throws up, or you can improve your grade in under an hour by checking out my awesome chemistry transformation playlists.